Bismillahirrahmanirrahim. Today, inshallah, we shall talk about isosceles and equilateral triangles. If you recall, isosceles triangles are those that have two sides that are congruent. So if I were to draw this triangle here, and like this, and if these two sides were congruent, that would be an isosceles triangle right here. So an isosceles triangle is a triangle that has two sides that are congruent like this. An equilateral triangle, of course, is one that has all three sides being congruent. So nevertheless, so with isosceles triangle, with the two sides that are congruent like that, they're given name. They're called the legs of the triangle. So here's a leg, and here's another leg. So an isosceles triangle has two legs, and this side over here, the non-leg side, if you like to say, that's called the base of the isosceles triangle. So an isosceles triangle has two legs and a base. Of course, it has three vertices over here, and the three sides. So the two congruent sides of an isosceles triangle are called the legs of the isosceles triangle. Now, the same terminology does not apply to equilateral triangle because all three sides are congruent. There's no base, there's no leg. All of them are congruent. So this terminology applies to only isosceles triangles. Now, in this section, we shall learn a theorem that is one of my favorite theorems in geometry. A very useful and very intuitive and very beautiful theorem, I think, and has to do with isosceles triangles. So let's dive into it, and then let's learn the theorems and do some examples using this. So here's the first theorem, and there's only one theorem, and then we have to learn its converse, really. So theorem. Isosceles triangle theorem, aka one of our most favorite theorems in all of geometry. The theorem states if two sides of a triangle are congruent, that means it is isosceles, right? So this is another way of saying, this is basically stating that if you have an isosceles triangle, if two sides of a triangle are congruent, then the angles opposite those sides are congruent, okay? So if I were to redraw my isosceles triangle over here, it's saying that if two sides of a triangle are congruent, that is, we have an isosceles triangle, then the angles opposite of them are congruent. So the angle that's opposite of this side is that, and the angle that's opposite of this side is this. So if the sides are congruent, then the angles opposite to the sides are also congruent, okay? So now the way we say that here is like this. You can write it symbolically like this. If the sides are congruent, right, then the angles opposite of them are congruent. So in writing proofs many times in the reasons column, when you're giving a reason, you can just write this symbolically, and it makes sense. And the idea being, if the two sides of a triangle are congruent, then the angles opposite of the sides are congruent. It's a very simple sounding, very beautiful theorem, and very useful, as I say. So if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So in this case, we have AC is congruent to BC, right? So AC is congruent to BC. So this side is congruent to this side. And notice how the statement is written. If AC is congruent to BC, then the angle opposite of AC is 2. Angle 2 is congruent to angle 1 because the pattern continues. The one that's opposite of AC is angle 2, and the one opposite of BC is angle 1, like this. So AC goes with angle 2 and BC goes with angle 1. But it doesn't matter which way you say it because of a symmetric property, but that's the idea. If AC is congruent to BC, then the angles angle 1 and angle 2 therefore have to be congruent. That's what this beautiful simple theorem states. If two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So that's it. That's the theorem that we should learn. This theorem has a converse, and it's just as easy. So this is the isosceles triangle theorem converse. That is, if two angles of a triangle are congruent, okay. Now this is interesting because here if two sides of a triangle are congruent, it's like saying, okay, you got isosceles triangle. But this is not as intuitive, right? Because if two angles of a triangle are congruent, then the sides opposite of those angles are congruent. In other words, if your two angles are congruent, then you got an isosceles triangles in your hand. You know what I'm saying? So if two angles of a triangle are congruent, then the sides opposite of those angles are congruent. If angle 1 is congruent to angle 2, then the sides opposite of those angles are congruent. If angle 1 is congruent to angle 2, then BC is congruent to AC. All right? So that's the converse of this theorem. Now, notice symbolically it's written like this. So if the angles are congruent, then the sides are congruent. So the isosceles triangle theorem and the isosceles triangle theorem converse are very useful. The isosceles triangle theorem starts out with an isosceles triangle. That is, if two sides of a triangle are congruent. That's why this is called an isosceles triangle theorem, because you're starting off with an isosceles triangle, and the converse starts with the angles. So if two sides of an angle are congruent, then this angles opposite of them are congruent, and the converse of the isosceles triangle theorem is if two angles of a triangle are congruent, then the sides opposite those angles are congruent. It's worth repeating a few times until you become comfortable with this. And symbolically, we just say if the sides are congruent, then the angles are congruent. And the converse of this is if you're given that two angles of a triangle are congruent, then the sides opposite of those angles are going to be congruent. So now this here is the isosceles triangle theorem, and this is the converse of the isosceles triangle theorem. This is the isosceles triangle theorem because you start out with an isosceles triangle, and here you end up with an isosceles triangle, the second in the converse of the theorem. So this is the only theorem that we learned really in this unit, in this section, and it's pretty easy. And we shall learn a couple of corollaries that go along with this in just a second. But first, let's practice on this a little bit. So here's a couple of figures that as illustrated in your examples in the textbook. And the idea here is marked two congruent angles, congruent sides that we can deduce from these figures using the isosceles triangle theorem. So let's look at this first triangle here, triangle ADC here. Let's look at this particular triangle. Our instructions here is to name two unmarked congruent angles and name two unmarked congruent segments. So unmarked angles that are congruent and unmarked segments that are congruent. So we're supposed to find two angles that are congruent that are not marked and two sides that are congruent that are not marked. So let's find some congruent angles. Well, here we have an isosceles triangle over here. All right, let's do that first one, actually. So here we have isosceles triangles. The isosceles triangle theorem says if two sides of a triangle are congruent, then the angles opposite of the triangle. So if this is congruent, this is congruent, then the angles opposite of them are going to be congruent, right? So these angles over here have to be congruent like this. Okay, that's the isosceles triangle theorem. If two sides of a triangle are congruent, then the angles opposite of them are congruent. So if you know this angle ACB is congruent to angle B, so you can say angle ACB, and here you have to be precise because there are two angles that stem from this vertex C. So you have to be very precise in how you name this. So angle ACB is going to be congruent to angle B like this. You can say that, or you can say angle ABC is another way of naming that. So we got that. So okay, what else can we deduce from this particular figure? Can we find two congruent segments that are not labeled? I think we can, because here we have two angles that are given to us that are congruent. And the converse of the isosceles triangle theorem says that if two angles of a triangle are congruent, then the sides opposite of them are congruent. So this side is going to be congruent to this side over here, right? So now this one is already marked with one tick mark, so we have to mark with the same one tick mark here like this. So these two sides are going to be congruent because of those two angles over here, ADC and ACD. So there we have it. So we deduce these angles to be congruent, and we also deduce these two sides to be congruent from the two theorems that we learned, isosceles triangle theorem and the converse of the isosceles triangle theorem. Okay, easy peasy. Now let's see what we can deduce from this particular figure. This idea here is the same. That is, we are to find two angles that are congruent that are not marked, and we are to find two sides that are congruent that are not marked. So in this particular figure, you actually have quite a few triangles. You have this baby triangle, and you have this baby triangle, and then you have this triangle over here, and then you have this triangle here. But there are actually even more triangles. Can you see more triangles over here? Well, here's another one. Here's another triangle. See that one? I'll show you. There's another triangle over here. How about this one here? Right? Do you see any more triangles? Oh, look carefully. Here's another triangle. See? And there's another triangle here. So there are quite a few triangles in this particular figure. So we have to make sure we deduce the right things, because sometimes you start seeing stuff that's not there in a way. So you have to be careful how you interpret the diagrams and make sure you use the theorems correctly. So anyway, so we're supposed to find two angles that are congruent. So what would we know? Well, isosceles triangle theorem states that if two sides of a triangle are congruent, then the angles opposite them are congruent. Well, here we're given two sides. But of what triangle though, right? Well, of this triangle, right? Not the baby triangle, but this particular triangle. So for those triangles, if that side is congruent to that side, then this angle has to be congruent to that angle. So you have to be careful which angles you deduce to be congruent. So if those sides are congruent, then the angles opposite of them are congruent. That's those little angles over there. So here we can deduce that those angles over here are congruent. Okay, very good. And the converse of the isosceles triangle theorem says if the angles of the triangle are congruent, then the sides opposite of them are congruent. So here we're given two angles that are congruent, therefore the sides opposite of them are congruent. So those two sides are congruent. Now this isosceles angle theorem and this the angle theorem like this. Okay, so if the two angles of a triangle are congruent, then the sides opposite of them are congruent. Sometimes this is called the base angle theorem. Okay, that's because this is the base, right? There are two base angles. So that's the leg of that's the leg, and that's the base. So you can call it whatever you want. That's base angle theorem. So there's isosceles. So this is the isosceles triangle theorem. This one here. This one is called the converse of isosceles triangle theorem, or the base angle theorem, whichever you like to see. The idea being, if you should really be able to articulate the theorem in your own words, if needs be, and that's the key thing, as a conditional statement, if and then. So if you should, for all the theorems that you learn, you should be comfortable articulating them as conditional statements. That's how you actually know your theorems. Okay. So this was just some basic practice questions before we move on. Well, what's the proof for this isosceles triangle theorem? Okay, so how do we know? Isosceles triangle theorem says if two sides of a triangle are congruent, then the two angles opposite of them are congruent. How do we prove that? It's a theorem, so we should be able to prove it, right? So here's a question that gives us an opportunity to do that. So we're given this triangle LMP. So here's triangle LMP. And we're told that LM, that's this side, is congruent to LP, this side here. So we have a triangle LMP with two sides that are congruent. That's we're given this particular situation. And then we are asked to prove that angle M is congruent to angle P. Right, so we're asked to prove. Now we can't say this is you can't use the theorem as the proof of the theorem, right? You know what I'm saying? Here we're trying to actually prove the theorem. So how do we prove the theorem to be true? Well, they give us a hint here. They draw this little dotted line, right? Okay, so you draw that little dotted line. So fine. So you have this particular dotted line. So then what? Well, if you have this particular dotted line, if you can imagine that you created little two baby triangles, right? This triangle over here and this triangle over here, then if you can somehow prove that those two triangles are congruent, then M and P would be congruent by CP, CTC. But this is just no ordinary line that they drew over there, right? What do you think about that line that they drew? Okay. What do you think about that line? Well, there's no ordinary line. That's a line that goes from point L to N, and N is actually the midpoint of MN, of NP. So you take MP, you cut it in half, right? So you find the midpoint N, and then you draw a line, because 2 points determine a unique line. So that's one of our postulates that we learned, right? So we draw this line LN, and then we create this particular segment such that you have two congruent segments here. So LN is a segment that connects from point L to the midpoint, that's point N. So now we have those two sides that are congruent. And then, you know, this side is congruent to itself. So now we have two triangles with three sides that are congruent to themselves, right? So you have this triangle and that triangle, and they're congruent to themselves because of side triangle congruence postulates. If three sides of a triangle are congruent to three sides of a second triangle, then the triangles are congruent. Once we've proven that the triangles are congruent, then these two angles are congruent by CPCTC. Corresponding parts of congruent triangles are congruent. So again, how did we prove the isosceles triangle theorem? Well, what we did was we drew a line that from vertex L to point N, which is the midpoint of MP. So we know those two segments are congruent. And we know by reflexive property that Ln is congruent to itself. Then we have two triangles like this that are congruent because of side triangle congruence postulate. And from there, we know that M is congruent to P because of corresponding parts of congruent triangles are congruent. And that's how we prove the isosceles triangle theorem. So you should write this out. In fact, this proof is in your textbook, and you should be able to actually do this proof on your own if needs be. Well, you said, well, this section is about isosceles triangle and equilateral triangle. We haven't talked about the equilateral triangles yet, right? So it's not very seeming. Well, let's talk about equilateral triangles. Well, there are corollaries of the isosceles triangle theorem. In other words, this theorem gives you more stuff that you can derive from it. So corollaries are basically theorems that you derive from other theorems. They're baby theorems in a way. So isosceles triangle theorem corollaries for equilateral triangles basically says if a triangle is equilateral, if and only if it is equal angular. See, let's say if you're given that this is isosceles triangle, right? So if it is equilateral, if you're given an equilateral triangle like this, then from the isosceles triangle theorem, then you know those two angles are congruent, okay? And because you're also given that this is an equilateral triangle, you can use these other sides to conclude that those two angles are congruent. Okay? In other words, if you're given an equilateral triangle, okay, like this, you can apply the isosceles triangle theorem 2 times using those two sides. And then you can also apply the isosceles triangle theorem using those two sides. And what you get from there is a triangle that has all angles that are congruent to themselves. Okay? So if you apply the isosceles triangle theorem 2 times to an equilateral triangle, then you get this. So again, if you have an equilateral triangle, you have an equal angle. So why do we know that equilateral triangle is equal angle? Because we can apply the isosceles triangle theorem to an equilateral triangle 2 times. So this is a corollary. That's something that you already knew, that equilateral triangles are also equal angular. And the reason for that is because we can prove that using the isosceles triangle theorem. There's a second corollary, which I just summarize it like this. Now, and all the angles have to be 60 degrees because the sum of the interior angles of a triangle is 180 degrees. If you cut them into 3, you get 60 degrees. So all the angles are the same and they are 60 degrees because the interior angles of a triangle add up to 180 degrees. So this is a corollary actually, or a result of the isosceles triangle theorem. All right. So there you have it. Now, let's do some questions. These are example questions from your textbook. Now, find the value of each variable. Okay, so here we're supposed to solve for the variable. We're given an isosceles triangle here, and somehow we're going to use the theorem that we learned. We only learned one theorem, right? So the theorem states that if two sides are congruent, then the two angles opposite of them are congruent. So, alright, we got that. But okay, so but we're given these two sides to be congruent, so we can solve for y easy peasy because they're going to be congruent right? So you have 4y minus 2 has to be equal to 2y plus 2 because they're congruent. I'm going to subtract 2y. I'm going to collect my variables to both sides like this, and you better check my math because I do sometimes make mistakes, more than sometimes. Alright, so here you go. And then I add 2 to both sides. I get 2y equal, add 2 here, 2 here. I get 4, and then I divide by 2. I get y is equal to 2. That was easy peasy. So we're asked to solve for the variable. That's not too bad. And then, okay, so this is going to be tricky. And I have to solve for this angle. Now, this angle is not 80 degrees, by the way, right? It's not, because that's not the fact that these two sides are congruent. That means this side is congruent to this side. That angle is congruent to that angle, not to the 80 degrees. Well, if this is 80 degrees, right, it leaves 180 minus 80, right? That's 100 degrees, right? That's how much is left over, correct? So if you remove 80 degrees from 180, left 100 and 100 degrees, and then you divide that by 2, this has to be 50 degrees, right? I hope you follow that, because the interior angles of a triangle add up to 180 degrees. This is 80 degrees. Take that away, you have 100 degrees left, and you have to divide them equally between these two angles. So that's 50. So this side has to be 50 degrees. So 6x plus 8, if I copied the question correctly, it has to be equal to 50 degrees. So 6x, subtract 8 from both sides, I get 42, correct? 6x, 6 times 5, 30, so 7. So x is 7. 7 times, divide both sides by 6. 7 times 6 is 42 last time I checked. So, that all. We did it. That was not too bad, I think. So we just used the isosceles triangle theorem to do an algebraic type of a question here. Okay, so there's one more question I want to do, and then I shall save it for next time, inshallah, but I just want to review before we finish here. Today we learned theorems and corollaries about isosceles and equilateral triangles. Suggested that the isosceles triangle theorem states that if two sides of a triangle are congruent, then the angles opposite of them are congruent. Angle opposite to those sides are congruent. And the converse of that, if two angles of a triangle are congruent, then the sides opposite of them are congruent. And there are, in short form of those, they're written like this conveniently. These are very, very useful theorems, and from this we derived the equilateral triangle corollary theorem that says that in a triangle, if a triangle is equilateral, if and only if it's also equiangular. So equilateral triangles have to be equiangular, because we can use the isosceles triangle theorem 2 times to prove that all the angles of the equilateral triangle have to be congruent. Inshallah, we shall build on this next time. Until then, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.